Okay, so let me start where we were last time. So we had just seen these kind of we saw sets as building blocks, and we had seen some constructions where we could take new sets and do something to them to make a new set. Okay, so we started just at the end of class. We had A and B were subsets of this set U, and we defined the union to be the X in U, where X was in A or X was in B. We had the intersection, X is in U, X is in A, and X is in B. So remember, or here always meant and or, so you were allowed to be in one or the other or both. For the intersection, you have to be in both of them. Then we had A minus B. This was X in A, where X was not in B. And then I'm going to just do one more, which was I'm going to call it a complement. So the C stands for complement. This is defined to be the X that are in U, where X is not in A. Okay, so a complement is just all the elements in X that you see, or all the elements of U that aren't in A. You can see now why it's kind of useful to have this universal set lying around, just so you can, define things like complements. Okay, so, well, maybe I won't draw all the pictures, but remember we had Venn diagram pictures for all of these. So I'm just going to make a note here. So the Venn diagram are useful for kind of understanding a concept. But you need to be careful when using them in proofs. And actually, I'm just going to say but should not be used in proofs. Okay, so the reason that they're insufficient for proofs, or why you have to be more careful, is because it really makes, there's a lot of assumptions about sets A and B. So we always draw, I'll just draw it again, we always draw set A and B to have a Venn diagram in this way. But of course you can have sets where you have A and B, and of course A could be containing B. So here might be A, B might be here. Or you might have A and B are completely disjoint from one another. There aren't any elements in both. And so, and there's more possibilities. B might be the empty set, right? So I might just see A here. And so if you are trying to write down, proof using Venn diagrams, you have to include all of these pictures. And that's just, not what you want to do. So we're going to introduce in this class, I'm going to give you the tools to write formal proofs that are careful and kind of encompass all of the possibilities of these pictures. Okay, so let me now go and play my favorite game again, which is, of course, true-false. So let's see. So the first will be A intersect B will be contained in A. A intersect B is contained in B. A minus B is contained in A. A minus B is contained in B. So notice all of these are sets, right? So it makes sense for me to use the containment symbol. Let me do one more. A complement union, A union B complement is A complement intersect B complement. Okay, so I'm going to say pause here, and then just check to see if you have the right answers, and then I'll provide them soon. Okay, so let's see. So the first let me try to be careful. So this one is true, 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 false, and true. Okay, so we can go over this pretty quickly. I mean, the first four are pretty easy. Okay, and the last one is definitely not. Okay, so that requires a little more proof. So maybe I'll just, so for example, if you wanted to prove that this is true, well, this is, what do you have to show? Let me do one. Okay, so if I wanted to show A intersect B is contained in A. So we have to show, and this will maybe seem, like too much work, but I think it'll be useful to give you a kind of structure for later proofs. So we have to show that for every x in A intersect B, x is in A. Okay? So what you do is you always, if you're trying to show something for all x in A intersect B, well, you should start with an element in A intersect B. So this is going to be a common feature of a lot of the proofs involving these, comparisons between sets. Okay, start with something there. What do we have to show? Well, we have to show it's in A. So by definition of intersection, x is in A and x is in B. So therefore, x is in A. Okay, and that's it. Okay, so therefore you get this. So since we did that for all x, and you might want to, I'm even going to add the proof symbol. You can even add a sentence at some point saying, like, since x was an arbitrary element, we know this for all x, but I'm just going to leave it for there now. Maybe I'll do this fourth one here. So this was 1, this was 4. So if I wanted to show that A intersect B, or A minus B, is contained in B is false. So I'm just going to make the one point that if you want to disprove a statement, all you have to do is come up with one counterexample. So we need one counterexample. That's it. So whenever you're proving something false, you don't need to prove anything about, all sets. It's just come up with two sets where this is not true. So I don't know, I'll say A is equal to the set containing the empty set, and B is equal to the set containing 1. Okay? And then A minus B is just A, and it's certainly not contained in B. Okay, but that's just a kind of a general useful thing to know. You need one counterexample to disprove, and then to prove, requires sometimes a little more effort. Okay, so it is true that, there are sets where 4 is true, right? So if A was a subset of B, this would be a true statement. But you just have to, you have to be careful when you come up with a counterexample, but once you have one suffices. Okay, so I'm now gonna work on this part, okay? So I'm gonna do the last statement, which is part of what's called De Morgan's law. And so to show equality, what we're going to do is show double containment. So we have containment this way and containment this way. Okay, that's by the problem that we talked about in the first lecture, or the second lecture. Okay, so let's, as a lemma, do that the complement of A union B is contained in A complement intersect B complement. And the reason that this is it's good to use double containment is that it gives you a nice framework for the proof. So if I want to show that this set is contained in this set, well, sorry, let me move this up. What I have to do is take an element in the set on the left and show X is in here. Okay, and since we chose an arbitrary element, that will show the containment. Okay, so what do we have? So by definition, we know that X is in U, and X is not in A union B. Okay, so that's the definition of complement. Okay, so now what does this mean? So I'm just going to, again, go by definition. By definition of union, so we still have X is in U. So if you're not in you're in the union if you're in one of the two. So it means that if you're not in the union, you are not in A, and you're not in B. Maybe I should even emphasize that this is and. Okay. So if you're inside a union, you have to be a member of at least one. So if you're not in there, you can't be in both. Okay? So what does this mean? Well, again, now by definition of complement, and I will stop writing this, and I'm very happy if you don't write it in your proofs. So we have X is in U, X is not in A, and X is in U, X is not in B, and therefore this means that X is in A complement and X is in B complement. Again, I could write by definition here, but this will be, so X is in A complement intersect B complement. Okay, so that's one direction, and I'll do the other direction as well. Okay, but you should, at this point, it's a good part to kind of think of questions, which I'll be happy to go over. Okay, so the second part, if we want to show this double containment, is to show that A complement intersect B complement is contained in A union B complement. So in this case, this will kind of have a similar flavor. In general, when you do different double containments, there's no reason for the proofs to be similar. In this case, it will. Maybe I'll even write proof. I should have done that here. Proof. So let Y in the set that we're interested in. Okay. So this means, so by definition, Y is in A complement and Y is in B complement. So what this means is, so Y is not in A and Y is not in B. Maybe I should say the reason I chose, Y is just to make it different from X. It doesn't really matter, but I already declared X to be in the set on the A union B complement, so I chose a different letter. Doesn't matter. So we have Y is not in there, and Y is not in there. So this means that Y is not in A union B, which means Y is in A union B complement. Okay? And therefore, since we have two inequalities, so we said, so since the complement of the union was contained in the intersection of the complements, and vice versa, we must have equality. Okay? Okay, so now I want to slightly change gears. And we're going to see, I mean, in the homework you'll see a lot more that you can do with playing around with sets and different constructions, different properties that they have. But I want to get to kind of the next thing, next part of doing mathematics, which is statements and sentences. So when you read math, So reading math, you will find it full of what's called, declarative sentences. And we've seen some already, right? Okay, which can be assigned truth values. Depending on whether the statements are true or false. Oops. I know my spelling is getting terribly now. Can assign truth values. Okay, so these are often called just statements. Or propositions, theorems. So let me just give you some examples of what they can be. So one could be, say, the 100th decimal of pi is 7. To be honest, I don't know whether that statement's true or false, but it can be checked, okay? And we can say that this statement is a true statement or a false statement. Maybe even some of you know, okay? One that's a little trickier, and is this sentence is false. So we have to be careful. You can't just write. Anytime that you write a statement or a sentence, you're probably going to incorporate some amount of the English language into the mathematics. And we've seen even on the first day that there was trouble with that, right? We had sets that can be described with, less than 20 words, and that was a huge logical issue. So this is, the even simpler logical problem. So we're gonna, you have to kind of make, set the ground rules for the statements that you can judge the truth or falsity of them. Another one might be something like this. So this is different, right? I'm just going to call it an open sentence, because its truth depends on the value of x. Right? So you might think, well, okay, we're going to be better if I say there exists. So I think I introduced this before, but I'll write there. There exists an x, so that x squared minus x minus 1 is equal to 0. But even here you have to be careful. Still depends. So this now depends on where x is. So what is x an element of? So in other words, you have to specify a domain for x. So if I said there exists an x in n, so that this statement, then this would be false. Right? There's no natural number that satisfies this equation. Even if I said there exists an x in the rationals, then this would still be false. Okay. But then if I said there exists an x in the real numbers, where x squared minus x minus 1 is 0, then we can all say, well, now we can do Pythagorean theorem, and we get x is, well, so it's still, so now this statement is true, and you can just plug in the golden ratio, or the negative analog of it. Okay? So in some cases, you just have to be careful about, if you're going to write about a sentence about an element, you should say where that element is going to be. Okay? So now again, you should think of these sentences or statements as building blocks. And just as with sets, we wanted things, once we had these building blocks, we wanted to do things with them. Similarly, for statements, we want to put statements together to make new statements. Right? So what can we do with a statement? So given a statement, what can we do? So the first thing, of course, is just check if it's true or false. That's a good thing to do. I mean, that's, sometimes that's hard, but, what could be better than that? Okay, what can you do after that? So let's try to put up here. So the next simplest thing might be to negate it. Okay, so what do I mean here? So let me give you an example. So P could be the statement, it is Tuesday. And the negation of the statement is, not P is the statement, it is not Tuesday. Okay, so this negation is true precisely when P is false. Okay, so that's what I mean by negation. They're never at the same time true for anything that you can verify. Okay, so let me give you another statement where we can check its negation. So Q will be the statement, every pizza has cheese on it. Now again, we're not checking whether this statement is true or false at this point, right? We just want to find what is the negation of the statement. Okay, so what would this be? And actually, this is a perfect time. I'm just going to say pause, try to write down this statement, and then I'll write it down in a second. Okay, so as you can see, I took the time that you were thinking to draw some pizzas. So let's see, what would be a tempting thing to say? Oops, I kept my cheese color. Let me switch back to my black. So this is the tempting thing to say, is that no pizza has cheese on it. Okay, but notice that this is not, so you would think that this would be the negation just because we changed the word every to, this is always true, this is always false. This isn't necessarily, this is not the negation though. So what is the problem? Well, we said the negation of a statement is true exactly when the statement is false, right? But in this case, I've drawn a pizza. One of them has cheese, and the other one doesn't. Has something on it, peppers and something. Okay. So this is false, right? Every pizza has cheese on it is a false statement. See, I just drew two pizzas. But on the other hand, the statement no pizza has cheese on it is also false because I drew the one with cheese on it. So that means that these are false at the same time, so therefore it's not the negation. So what is the true answer? It's that there is. So every goes to there is a pizza with no cheese on it. Okay, so in general, you have these for alls generally go to exists whenever you want to negate something. You can think of this as similar to if you want to disprove a statement, you come up with one counterexample. Well, here's a statement that I made about all pizza. Every single pizza has cheese on it. So, to disprove it, I have to prove that the negation is true, and that means I just find a single pizza with no cheese on it. Okay, so let me go to the kind of the most important relation between statements. I'm obviously going to leave the pizzas in the picture. So the most important relation between two statements is implication. Okay, so I'm gonna give this a formal definition. Okay, so the definition is for statements P and Q. The implication is the statement if P then Q. So is the statement if P then Q, we also write P implies Q, or say P implies Q. So this is generally thought of as the hypothesis. So you're saying if this is true, and this is the conclusion, then that is true. Okay, and it will be always denoted by P arrow Q. So here's something that we have to be careful of. It came up even when I was first introduced the empty set. Okay, so when is this statement false? I'll just say that. So this is false, well, when P is true and Q is false. Okay? So P implying Q is a false statement if P is the true statement and Q is a false statement. That's, very believable. What's slightly trickier is that it is defined to be true in all other cases. Okay, so it doesn't really care what happens. So it doesn't care what happens if P is false. Okay, so if you're starting with a false conclusion or a false hypothesis, then any conclusion is said to be true. Okay, so let me give you some examples here. So examples. Okay, so the first one can be, it is raining implies I will get wet. Okay, so notice this is, whether it's true or false probably depends on whether I'm inside or outside. And also depends on whether it is raining or not. So if it's a sunny day and you're saying it's raining so I'll get wet, then that is true, except, it's a sunny day. So it doesn't tell you too much. So let me give you my favorite example, I guess. I don't know why it's my favorite, but if I smoke, then I will look cool. Okay, and we're just going to play around with negating this and coming up with some equivalent statements. Okay, so again, whether it's true or not depends on whether P and Q are both true. So maybe I should say this is P, this is Q. So let's think about what is the negation of P implying Q. Okay, so I want you now, again, this is a great point, just pause. Think about what the negation is going to be, and then try to just write down the sentence, and we'll see if we come to the same answer. Right, so let's work through what we should get here. Okay, so let's think about when is P implies Q false, because that will tell us when the negation should be true. So P implying Q is false only when, so P is true and Q is false. Okay? So what does that mean here? Well, the negation of P implying Q is then true only when P is true and Q is false. All right, so what does that mean? Well, it means that the negation of P implies Q is the statement P and not Q. So P is true and not Q is true. Okay, so this is kind of something to be careful of. It's very tempting to think that the negation of an implication statement is another implication statement, but that's not the case. Okay, so and you can think about that as saying, well, this is kind of, if you write down the truth tables, then there's, P could be false or true, Q could be false or true. You have 4 possibilities. One of those possibilities gives you something false. So therefore, only one of the possibilities for the other one should be giving you something true. And that's what P and not Q does. Okay, so we'll write this in an example, but I'm just going to give one more kind of statement. Okay, so there's kind of a weird way to rewrite P implying Q, okay, which is called the contrapositive. And what that is that it's not Q, implies not P. Okay, so why are they the same? Well, now I'll just say P implies Q is true unless P and not Q, right? This is what we saw for the negation. So it's true unless we have this one case where P is true and not Q is false. Not Q implies not P is true unless not Q and not P. Okay, so I'm just writing exactly when the implication is false here. But this is just P. And now we have exactly the same thing. So you can check the negation of the negation is just the original statement back. So you get that this is the exact, has the same, it's not the same exact statement, but it's true exactly when the other one is true. Okay, so do not confuse this with Q implies P. Okay, I'm going to write, this is a very common mistake. But this is not, we'll see just in an example that this is not the same, these aren't always the same statement, but these ones always, the contrapositive always is. Okay, so I'm just going to, okay, so let me do my favorite example. P implies Q if I smoke then I look cool. So what is the contrapositive? If I don't look cool, then I don't smoke. Maybe I should have said if I'm smoking, then I look cool, but that's too hard for me to work out. Okay, so and notice these are the same statements, right? So if this is true, if I smoke, then I look cool. Well, if I don't look cool, then for sure you know that I do not smoke. Okay? Because otherwise I would look cool. So let's do the converse. Q implies P. That's just a statement, if I look cool, then I smoke. Okay, but notice this is not the same, right? As P implies Q, I could look cool, but you know, for totally different reasons, right? I could have be wearing a cool T-shirt. Okay, so just the fact, so if I know that if I smoke I look cool does not tell you anything about, in general, about going the other way. Okay. So let me see. Finally, just one more thing which is kind of useful. P if and only if Q. So this is true if P implies Q and Q implies P. Okay, so these are, we think of them as equivalent statements. So you might say this is kind of silly. I mean, we're saying P implies Q. If P is true, then Q is true, and if Q is true, if P is true, why are we doing this at all? So it's useful to characterize, well, just say something in terms of something else. Okay, so what do I mean here? Let me just give you an example. A differentiable function is increasing if and only if its derivative is positive. Okay, so these are just equivalent statements, so you're not really learning anything new. On the other hand, this obviously is telling you some interesting behavior of this derivative function, right? So it's telling you, or the original function, right? So there's interesting relations, even though they're true if and only if either one is. Okay, so I'm going to stop here and see you in discussion.